All right, welcome back to Math 465. This is Friday's lecture, Friday, September 8th, I believe. And we didn't quite finish section 1.2 last class. We defined parameterized differentiable curves. We saw a few examples. We talked about how what the tangent vector corresponds to geometrically. In the book, if you've read the section, they do a quick reminder or a quick sort of overview of the dot product. So I'll just say a few words on that right now. So let's do blue. So say I have two vectors in R3, and of course this works in any dimension. Say U1, U and V. Okay, these are both vectors in R3. Then the dot product is defined as U1 times V1 plus U2 times V2. So we just multiply the components up and we add them together, of course. All right. Okay. And it satisfies the following properties, which I guess I will list as a proposition here. Okay, for all U, V, and W in R3 and all scalars lambda, we have the following properties. The first is that the dot product is commutative. The second is that if we take two vectors, take their dot product, and then multiply the result by a scalar, that's the same thing as multiplying the first vector by that scalar and taking the dot product, or multiplying the second vector by that scalar and then taking the dot product. Those are all the same. The third property is that the dot product distributes over vector addition. Okay, and the fourth property is that although the dot product of two arbitrary vectors can be negative, the dot product of a vector with itself is always non-negative, and if U dot U is equal to 0, so a vector dot itself is always non-negative, and if the vector dot itself is equal to 0, that happens if and only if U itself is equal to 0. Okay. So we say that two vectors, U and V, are orthogonal if U dot V is equal to 0. So that's how we define what it means to be orthogonal. And the length or norm of a vector U in R3 is defined as just the square root of U dot itself. Okay, which really is just sort of the Pythagorean concept of distance. Okay, it's this idea of distance that you get from Pythagorean theorem. Okay, and finally, for all vectors U and V in R3, we have that the dot product of U and V is equal to the norm of U times the norm of V times cosine of theta, where theta is the angle made by the vectors u and v. Okay, so in other words, if you draw the vectors u and v, which, I mean, really they're just points in R3, but if you connect those points to the origin, then you get two arrows that are connected to the origin. Those two arrows lie in some unique, there's a unique plane that contains both of those arrows, provided that they're not parallel to each other, and the angle made between those two vectors in that plane is the angle theta. Okay, and so really the dot product, you think of the dot product as providing some measure of sort of the collinearity of two vectors. So if two vectors sort of point in the same direction, then theta is small and cosine theta should be close to 1. So if two vectors sort of point in the same direction, then really the dot product should just be the product of the lengths of those two vectors. If they point in opposite directions, then cosine of theta will be -1, in which case you'll get negative the product of those two vectors. And if the two vectors are orthogonal to each other, then the angle they make is 90 degrees and cosine of 90 is 0. So sort of orthogonal vectors are sort of have 0 dot product, and the dot product increases as the vectors sort of become more collinear, or as they start to point in the same direction. Okay. So presumably this is all review from linear algebra and probably some other courses you've seen it in. What may not be review is the following, and this is just sort of a fact that the book points out, which we'll kind of use later. So note, oops, that's not my pen. So note, if alpha, say I have two curves, say alpha t, these are like parameterized differentiable curves, so let's call this xt, yt, and zt, and let's say beta is another one, and let's say it's u, v, and w. Okay, and these are two, so let's say if these are two parameterized differentiable curves, then essentially these are, for every t value, this is just going to be a point in R3, and this is just going to be another point in R3. So for every t value, you can actually take the dot product of alpha t with beta t, okay, because both alpha t and beta t are just points in R3, and that gives you a function. So this is a function from the interval. Now originally this is a function, this is a function from the interval to R3, and this is a function from the interval to R3, but because we're taking the dot product now, this is a function from the interval to the reals. Okay, where I guess I is the interval, I is the, so if I take, oops, that was weird. Sorry, I guess I recorded, I don't know if you guys could hear that, but I accidentally recorded a little bit of myself in Notability and then played it back, and that kind of threw me for a loop. So hopefully you didn't hear that, because that was rather jarring there. So the point is that both of these are functions from the interval I into the reals. Maybe I should have said something like, these are two parameterized differentiable curves with domain equal to I. Then we can take the dot product of both of these curves at any point we want, and for each point in I, we are going to get we're going to get two vectors in R3, and we're going to take the dot product of those. That's going to give us a real number. Okay, so this is just a real valued function on the interval, so we can take the derivative. Okay, and what does the derivative look like? Well, we take the derivative of that, and to take the derivative of that, we need to sort of write down what, we're going to take, what is this dot product here? So the dot product is just xt, ut, plus yt, vt, plus zt, wt. Okay, we're taking the derivative of that. And of course now we're just going to take the derivative of each of these individual terms. So when we take the derivative of this, because it's the product of two differentiable functions, we have to use the product rule there. So that's going to give us, I'm going to give myself plenty of space here, that's going to give me x prime t u of t plus xt u prime of t, and then we're going to take the derivative of this second term here. So that's going to be, again, using the product rule, y prime of t vt plus yt v prime of t, and then taking the derivative of that last term, it's zt prime of t wt plus zt w prime of t. And I'm running out of room there. Okay, so what we can do is we can regroup this actually, and we can split this up. So we can take the first three terms here, and we can write this as the dot. Well, sorry, actually, we're going to take this term, and this term, and we can write it as the dot product of alpha prime. So this is just x prime t, y prime t, z prime t, dot ut, vt, wt. So we've just sort of split out, taken these three terms, and we've sort of just split it up as a dot product. And now we'll do the same thing for the remaining three terms, plus this is going to be xt, yt, zt, dot u prime of t, v prime of t, w prime of t. Okay, and at the end of the day, that's just the same thing as alpha prime of t. That's this part here. That's just alpha prime of t. This thing is just beta t. And then over here we have alpha t dot beta prime of t. Okay. So what should sort of what this should look like is, it should sort of look like, I mean, not sort of, but actually quite reasonably so. This is really just kind of a product rule, right? I mean, if these were just two real valued functions instead of two functions into R3, and this was just sort of ordinary multiplication, then this is exactly what the product rule would look like. So in fact, we sort of have a product rule for dot products, which is kind of a nice fact. All right, so that kind of does it for section 1.2. We'll kind of move now on to section 1.3, or 1-3. I think they use dashes. And this is a section on regular curves. Regular curves and arc length. All right, so let's give that the respect it deserves. Let's underline that title. So let's let alpha be, some parameterized differentiable curve. All right. Now, let's talk a little bit about the tangent vector. We saw with this graph example last class that when you take the tangent vector of a curve, it's going to give you a vector which is parallel to the tangent line to the curve at that point. Okay, so again, we get a vector. When we take the tangent vector, we get a vector that's sort of situated at the origin. But if we were to translate that vector over to the curve and place it so that its tail lives on the curve, sort of at the relevant point, then that vector would point along the direction of the tangent line to the curve. Okay, so we're just going to make this a little bit more precise. So if t naught is an element in the interval I, and alpha prime of t naught, suppose this is not just the zero vector. Well, if that's the case, then the tangent line to alpha at the point t naught is the unique line in R3 which passes through the point alpha t naught and is parallel to alpha prime of t naught. Okay, so if if we draw a picture here, we've got our curve, right? We've got some point t naught. If we compute the derivative of the curve at the point t naught, we're going to get some vector over here that should be pointing roughly in this direction. If we translate that over here, we get some vector that's tangent to the curve at that point. And what we're going to look for is we're really just looking for the line that passes through that point and is parallel to this vector. Oops, let's erase that. Okay. So it's exactly what you think the tangent line should be. It's the line that passes through the point on the curve and is and whose direction is the same as the tangent vector at that point. Okay. Now the problem is that if the derivative vanishes at t naught, if the derivative of the curve, the tangent vector to the curve is 0 at t naught, then there is no well-defined curve. There is no well-defined line through this point. Okay, because if the vector is 0, then there's no way to find a well-defined line through that point pointing in that direction. So, if alpha prime at t naught is equal to 0, there is no well-defined tangent line to alpha at t naught. Okay? And this is kind of something that we don't want to happen. Okay? And I'll say maybe a word about that in a minute here. But let's see an example. Let's let alpha be a function from R. So this is a parametrized differentiable curve. Let's define it by alpha t is equal to t cubed t squared 0. Okay. Then we can easily sort of take the derivative. Then alpha prime of t is just equal to 3t squared 2t 0. Okay. Then we can really take any point we want and try and find the tangent line there. So, for example, then at t equals 2, alpha prime of 2 is equal to 3 times 2 squared is 12, 2 times 2 is 4, comma 0. And the tangent line, we can find the actually find the equation of the tangent line. So say we let S be the parameter for our equation line. So we can write down the equation of this line with parameter S just as alpha of 2 plus S times alpha prime of 2. So this is just 8. Alpha of 2 is just 840 plus S times alpha prime of 2, which is 1240. And when we combine them, we just get 8 plus 12s in the first component, 4 plus 4s in the second component, and 0 in the third component. So this is sort of a parametric equation form of the line. Okay? And you could find, you could find sort of an equation in terms of x, y, z if you wanted, but this is an equation of the tangent line to the curve at the point t equals 2. Okay? And we just found it by picking a point and then finding the direction of the curve of the tangent line, which is just the tangent vector direction, and multiplying that by some parameter. Notice though, if t is equal to 0, then when we plug that into alpha prime of 0 is just equal to, so remember, alpha prime of t is just this, so we're going to plug 0 in everywhere, and we get 0, 0, 0. Okay? And because of this, there is no tangent line to the curve alpha at the point t equals 0. Okay? So if we draw this, what does this look like? Okay, so this curve inside sort of the xy plane, so the z coordinate is 0. So really everything that we see going on with this curve is just sort of happening in this xy plane here. Okay, so I'm going to draw it the best I can, but it's going to look something like this. This is all happening in the xy plane here, where this is x and this is y, and this is z. Okay. So at the point t is equal to 2, we get some nice well-defined tangent line here. Okay, no problem. However, at t equals 0 is where we have this cusp, and that's why, because we have this cusp, we don't really get a well-defined tangent, right? It kind of looks like the curve is sort of pointing in like this, but it also sort of pointing in like this, and so because there's sort of this sharp turn, we don't get a well-defined tangent. Now, it's important to remember that this curve is a parameterized differentiable curve. So this is a smooth curve at that point, but it doesn't look smooth. The trace doesn't look smooth because it has this place where the derivative vanishes, okay, or where the tangent vector vanishes. So ultimately, if we want to sort of have things like tangent lines and to have those things available, we really need to have non-vanishing tangent vectors, okay. So, so we actually sort of will bake this into a definition. Okay. Okay. A point t in the interval I at which alpha prime of t is equal to 0. Okay, so if we have a point on our curve where the tangent vector is equal to 0, this is called a singular point of the curve alpha. Okay, and generally speaking, we don't want singular curves. Okay, so a parameterized differentiable curve alpha is called regular I'm going to actually write it slightly differently. So parameterized differentiable curve alpha with domain I, okay, is called regular if it has no singular points. In I. All right. And so essentially we want to focus on curves that don't have singular points. Okay. Now singular points can be interesting, especially when you're talking about surfaces and stuff, and they're worth studying. But for the stuff that we'll be doing, we really will need to sort of restrict ourselves to only have sort of regular curves. And so so we'll restrict ourselves to studying regular parameterized differentiable curves. Okay, but we'll often just call them curves. Okay, we don't like all those adjectives there. It just makes it too hard to say. So when I say a curve, unless I specify, we're going to be talking about a parameterized differentiable curve, a regular parameterized differentiable curve. Okay. So now we want to sort of talk about arc length. So let alpha be a curve. Now remember, when I say curve, I mean regular parameterized differentiable curve. And let's let t naught be some element in the interval. Then we can define the arc length. The arc length of alpha of t from the point t naught is a function which we'll call s of t. This is just the integral from t naught to t of the absolute value of alpha prime of u du. Okay? And here, where this absolute value expression is just the square root of u1 prime of, sorry, let me erase that. This is just x prime of u squared plus y prime of u squared plus z prime of u squared. Okay? And here u is just a dummy variable of integration. We were already using the variable t, so we needed to introduce a dummy variable there. Okay? So essentially we're taking the tangent vector at every point along the curve. We are finding the length of that tangent vector, and then we're integrating it along the curve from the point t naught to some point t that we care about. Okay. Now the choice of t naught, it only changes. We call this the arc length function. I guess we've defined that there. But really, by changing t naught, all we're doing is we're changing this function by some shift. And so oftentimes we really care about the derivative of this, and so we don't really have to focus on what that t is there. Okay. Now I think in Calc 2, if you took 113 at BYU, you will have sort of seen how this formula is derived. Essentially, you sort of take your curve, you have some curve, and you sort of start to approximate it using some like straight segments, and these straight segments are sort of somehow given to you by the tangent direction, and that by figuring out the length of these segments and adding up those lengths, it gives you an approximation to the arc length. And if you sort of let those segments get shorter and shorter, your approximation converges to the arc length. So presumably you've seen that before, and so this is just sort of the formula that allows you to compute the length of the curve. Okay. So one interesting thing to note is that if you take the fundamental theorem of calculus, which we all remember and love, by the fundamental theorem of calculus, we can actually try and take the derivative of this arc length function. Okay, so notice by changing the value of t, we're changing the upper bound of integration, and so therefore the integral will change. The value that we get when we integrate will change as we change t. Okay, which really just tells me that this is a real valued function of the variable t, and so we can try to take the derivative of t, and because of the specific form of this function, because this function is defined nicely in this way as an integral, we can take that derivative. We'll be successful when we take that derivative. And if you remember your fundamental theorem of calculus, essentially when you take the derivative of an integral like this, where the upper bound is the variable that you're taking the derivative with respect to, then essentially these two things cancel, and we just replace the u with a t. So this is just the absolute value of alpha prime of t. Okay? So the rate at which this arc length changes is actually just given by the length of the tangent vector. Okay? So if we draw a picture here, we've got some curve, and as we allow our parameter, so our parameter t lives inside some interval, right? And as we allow our parameter to sort of go through the interval, our point is going to move along this curve as we allow t to move over the interval, okay? And sometimes it's going to be moving faster, sometimes it's going to be moving slower, but if we sort of let t range at a constant rate over the interval I, we're going to see that our curve sort of speeds up and then slows down, then speeds up again, etc. And the speed at which it's traveling, or the speed at which the length is changing, the length of the curve is changing as we move along it, is really just given by the length of the tangent vector. Okay? So the tangent vector is somehow telling us how fast we're traveling along the curve. So now there are a particularly nice family of curves. Suppose now that alpha prime of t is just equal to 1. Okay. In other words, our tangent vector is always a unit vector. Okay. Well, if that's the case, then we can actually compute the arc length function directly, because this is just the integral from t naught to t of alpha prime of u du. But this thing in the middle here is just equal to 1. So this is just the integral from t naught to t of 1 du. And when we integrate that and plug in our bounds of integration, we get t minus t naught. Okay? So essentially, in this case, what's happening is the arc length function, which measures sort of how long an arc is from the point t naught. Really, this arc length function is just measured by the parameter distance. So how far away t is. So I guess what's one way to look at this? Well, if I have my curve here, right, and I have my parameter space here. So this is just I, and this is like alpha of I. Somehow, when I look at my input values, if I take sort of two input values that are like distance, say 1 apart, then if I measure the distance between, say this is like A and B, this is alpha A, alpha B, then if A and B are distance 1 apart, then the length of this curve is going to be precisely the length of this curve between alpha A and alpha B is going to be 1. Okay? Or if I take 2 points that are like, if I take 2 points that are like 1/2 apart, say this is U and V, then their corresponding points on the curve, alpha U and alpha V, if these are 1/2 apart, then this distance along the curve is going to be 1/2 as well. Okay, so in other words, this arc length, or sorry, if I have this really nice property here, then the arc that we have is really preserving the distance. So it's taking the distance in the parameter space and it's preserving it when it maps into there. Okay, and so we often describe this as saying, that alpha is parametrized by arc length. Okay, in other words, the parameterization here is just measuring the distance of the curve. And so sort of the distance in the parameter space is the same as the distance in the arc itself. Okay. So these are really nice curves that have this property, and a lot of times it's convenient to actually assume that the curve we're looking at has this property, meaning that it travels at unit speed, or it sort of has this nice property of preserving distances. And so it turns out that we actually that it's not, if I give you a nice regular parameterized differentiable curve, you can always sort of find one. We're going to see later on that you can always find one that's parameterized by arc length. So if really what you care about is the underlying curve, you can find a curve that's parameterized by arc length that has the same trace, I should say. So if really you're interested in the curve itself and you don't care so much about the specific parameterization, you can always switch to a parameterization for which is parameterized by arc length, which is a nice property, and we'll see that a little bit later. So that's about it for today. I think I've been going for almost 40 minutes here. So I'm going to wrap things up. Again, I'll be in class on Monday, so if you have any questions, feel free to shoot me an email. We can either find a time to meet over Zoom, or I can answer it over email, or we can talk about it when I'm back in class on Monday. But have a great weekend, everyone.